Hey guys, welcome to a new video in this algorithm and data structure tutorial. In this video we're continuing talking about trees which we have already been over in some of the previous videos when we talked about the priority queue, where we used a binary search tree to implement a priority queue. In this video we're going more in depth with trees, and we're also going to look at different types of trees that we can have and some different kind of methods that we can use in trees and why we're using trees in algorithms and data structures. So first of all, I'm going to give you an overview over what trees are. And we have like a tree. We can think of the tree like a real life tree, where we have like these leaves here on the tree that goes out from the tree in different sub trees, if we can say that. And we have those different types of trees that we're going to talk about in this video and in the next video, where some of them have different properties. And we're mainly going to focus in this video on the binary search tree, which is very important to know, and also like how to use it in algorithms and data structures. And then we're going over like the time complexity of a binary search tree, and we're going over like some balancing in trees, and also like how we can traverse in a tree. So if we're talking about trees, they have like, it's a data structure and it has this tree architecture. So we have like some root node up here, and then we have some subtrees here. So this over here is some nodes that is inside a tree, and then one tree can have like multiple subtrees inside of it, and then we say that the last nodes here are the leaves of the tree. So they have like this real world tree architecture. So it is a recursive data structure, so we can like divide our problem down. So we can like recurse down here in like the levels or like the depth in our trees. So this will be a recursive data structure, and often like when we're using binary search trees, like we're just halving the problem, and because we can list like if we're going to look up an example like a number, like we can either like look for it in the left subtree or the right subtree, because we have this tree architecture that is divided in multiple subtrees, and then we have some knowledge about that we can use for insertion, finding, and stuff like that. So that there are a lot of different kind of applications for trees, and some of them are also like very important. So a file system could, for example, be based on a tree architecture where we have like the folders here in a file system, and then each folder here can contain folders or files, which will just be like nodes inside of that folder, or like nodes in a subtree. And then we can also like have it for compiler, design, text processing, some search algorithms, as we're going to talk about when we're going to use binary search trees as well in this video. And then we also have like priority applications, as we implemented binary search tree as a priority queue, and we could then use that for some different kind of priority applications. And also in C++, the sets and the maps data structures, they're based on trees, and they're very widely used in C++ when we're working with like bigger applications, and we want this tree architecture in our application. So we need to know some of the basic concepts in the tree to like get a better overview or what it is and how we can use it. So first of all, we have a node here, which is like all these circles here are a node in the tree, and then the node contains an element of data. And then we can have an edge here, which is this black line here that connects the two nodes. So it's a connection between the two nodes, which we call an edge. And then we can have the root, which is the entry point of the tree often, and it is the top node. So this will be the root node of this tree here, and then these root nodes here are subtrees of this root node here. So we can also like have this child and parent architecture. So we have a parent node here, for example, and then this parent has two child nodes down here under. And when we're talking about binary trees, like they can only have two siblings, a maximum two siblings, because we have a binary tree which is either 0 or 1, so we only have two possibilities. And we can also like have leaves in our tree, which is just the nodes without children, or the nodes at the lowest level. So it will be like the 4 circles, or like the 4 nodes down here in the bottom. It will be the leaf nodes of this tree here. And then we can also have a path, which is the rope between two nodes. So let's say, for example, we want to find the path from this node here to this node, then we can have like a path going from this node to this node, and then down here in the left subtree here to get the path between two nodes. And we also have like a path length, which is the distance measured in number of edges between the two nodes. So it is, for example, like if we were here, like we can then calculate or like measure the distance or like the path length, which will be this node here plus like this edge here plus this edge here and this edge here. If we want to, like, let's say we want to go from a node C here to node D, then we can go in this path here and then measure or like calculate the path length. We can also have depth in a tree, which is the distance from the node to the root. So let's say that we're down here at the lowest level, or like at level 3 in this case here. Then we have like 2 levels up here to the root node here. So we say that the depth of this node here is 2. So it is the distance from the node we want to like get the depth of to the root node. And we can also have the height of the tree, which is the longest distance from the node to leaf. So let's say we want to get, like, for example, the height from this node here, and it is then the distance from this node here to the leaf. So in this case here, the height of this here will be 1. When we're talking about trees, we need like some kind of way we can, like, how we can traverse around in the tree. And we have 3 different types here where we're talking about in order and pre-order and post-order tree traversal. So when we're talking about tree traversal, we're talking about like how we want to traverse around in our tree here. So let's say we want to take the approach here in order, then we're first visiting all the nodes in the left subtree. So in this case, it will be these nodes here in the left subtree, in this subtree here, because this is the left subtree here, and then we have the root node, and then we have the right subtree here. So then we will have this subtree here, and then we will again first visit the left subtree here, which is only this node, and then the root node, and then the right subtree here, where again we want to visit this node first, and then the root, and then the right, if we took this in order traversal approach. And then when we are done with traversing this left subtree here, we can go to the root node, traverse from the root node to the right subtree, and then reproduce like the procedure we did for the left subtree as well. So this is like how we can traverse around in the tree, and we have these 3 different types here, where we also have the pre-order, which is just where we're starting at the root node, and then we're traversing over in the left subtree, and then we're traversing the right subtree after. And the last one is the post-order, which is we're first having like the left subtree, we're traversing the left subtree, then we're traversing the right subtree, and then we're ending at the node. So these are just some different kind of approaches of like how we can traverse around in a tree and do some different kind of operations. We're going to implement in order in later in this video in a code example, where we're going to implement in order to like order or traverse our nodes in the tree for finding nodes in our tree, or like deleting nodes and stuff like that. So we have different kind of types of trees, and we're in this video we're talking about mostly about binary tree and the binary search tree, and then in the next video we're going more in depth with AVL trees and what different kind of what differences there are on these types of trees. And we also have something called a B tree and a red black tree, but I'll come back to that in later videos and go more in depth with some of those trees here, because they have some other different kind of properties that can be used for some different kind of situations. So let's now talk about the binary tree, where in a binary tree each parent node can have at most 2 children, because we're talking about binary numbers. So we only have these 2 possibilities. It can either be a 0 or a 1. And we also have these different types of binary trees, where first of all we have this full binary tree, where the binary tree can only have the parent nodes of the binary tree can only have 0 or 2 children. So in this case here, to the left down here, we have a full binary tree where each parent node here has to have 0 or 2 children. So in this case here, we can see that this parent node has 0 children, and this parent node here has 2 children, and same with this parent node here. So it has to have either 0 or 2 children, like one of the parent nodes can't have 1, then it won't be a full binary tree. We can also have the perfect binary tree, where all internal nodes have 2 children and the leaves are at the same level. So down here in the middle here, we have an example of the perfect binary tree, where we can see like this internal node here has 2 children, and also this internal node here, and they have to, and all the leaves, they have to be at the same levels, which we can see down here as these 4 leaf nodes here are at the third level. So and we can also have a complete binary tree where like all the levels are completely filled except possible the lowest ones. So like we need to have like this kind of like perfect binary tree here at the top, but at the bottom here we have this we have the possibility of that we can have the lowest one here that is not filled, and like the last level of a tree here. So in this case here we have we have a complete binary tree here, and then if we were going to add a number or like add a node to this tree here, we will add it here because we add it to the left in our complete binary tree. And then if we add a node here again to the left, then it will now become a perfect binary tree. So when we're adding nodes to our complete binary tree, then we're adding it from the left to the right, and all the leaves are completely filled except possible like the lowest level, which are filled from left to right. We can also have a balanced binary tree which is just like the height of the tree and the right subtree do not differ more than 1. So it will be like balanced, so we won't have like a bigger left subtree than compared to the right subtree, so it will be balanced around the root node, and we can use that for some different kind of stuff. And we also almost like all the time want a balanced binary tree, or some of the other like binary trees here that we can then apply some application to. And we also have this binary search tree here, which is where we have this balance condition here. So we have like this balance condition here from the left subtree to the right subtree. So we have like some kind of balance. Then the depth of the tree is O log of n. So we have this time complexity for searching in the tree, because the depth of the tree is O log n. So that applies that the time complexity for searching in a binary search tree is also log of n, which is kind of fast compared to some other data structures that could probably have like linear time, where we have to go through all the like the whole array if we're going just applying a linear time complexity algorithm or like searching algorithm. Where in this binary search tree here, we know that if we're going to search a number, like we can either search in the left subtree or right subtree, and then we like divide our problem, and then our time complexity would be O log n. So in a binary search tree, the left child node is less than the parent, and the right child node is greater than the parent. So in this case here, we can see, like for example, if this is the parent node, then the left child node is less than the parent, and the right child node is greater than the parent. And the same applies in all of like the subtrees here, where 3 here, like 1 is less than the parent node here, and 6 is bigger than the parent node in this case here. So this is like how we can set up a binary tree, and then we can use these properties to like do some different kind of searching in log n time complexity. So the time complexity of binary search tree is what we talked about, log n. So we have these 3 methods here that we're going to implement in code, and I'm going to show you like how we can implement in code and play around with it in C++. So we have this search, insert, and delete method, and the binary search tree has like pretty good time complexity. So we often like use binary search trees for some different kind of purposes, as I already showed you in the priority queue video, where we can have some different kind of applications that could benefit from using a binary search tree, where we have this pretty good time complexity operations. So the space complexity for the binary search tree is also n of O of n, so it's linear space complexity as well, because we can just apply like, or we can just implement our binary search tree in as a vector or like some kind of array. And down here we just have like some table here that shows like the time complexity for the different kind of operations, where we can see that the average case is log n for both searching, insertion, and deletion, where we can have like this worst case complexity here, which just happens once in a while, and it will still be linear and better than some of the other data structures that we know of. So we're not doing this Sublime Text here, and I'm going to show you how we can implement binary search tree in C++, and some of the operations that we talked about in the slides as well. So first of all, we're going to create a structure here that contains the data of the node, and then it also contains a pointer to the left and the right child of that node. And then we have a function here to create a new node, where we give it the data or like the item that we want to give to the node, and then we just allocate some memory, and then we initialize our data and set it equal, like the data equal to the parameter or like the argument that we pass to our function here. And then we initialize the left pointer and the right pointer to the children to 0 or like to null, because we're going first of all, if we're just going to create a new node, it won't point to any children yet. And then we have this method here, in order traversal, if we want to like traverse around in our tree. So we have these 3 different types of traversal, where we're going to implement this in order traversal here. So this in order traversal here, it takes a pointer to the root node of our tree, and then we just check if the tree is empty here, and if it's not, we go through like this again here. So we go through all the left subtree here, like all the left subtrees here first, and then we traverse the root after we have been traversing all the root nodes in the left subtree, like all the nodes in the left subtree, and then we traverse the root, and then after that we traverse the right subtree in a traversal here, and then we have been through all the nodes in the left subtree, the root node, and the right subtree, and then we have done this in order traversal, and we have traversed around in our tree. So we also have this function here to insert a node, and then this function here, it takes the node that we're going to insert, and then the key, like the key that we want to insert, and then it will return a new node if the tree is empty. So if our tree is empty, we just return a new node, and we now create a new tree. Or else we traverse to the right place and insert the node, because we need to insert it at the lowest level in our tree. So we check if the key is less than the node key here, and if it is, we know that we have to set it to like the left child. We insert this node here in the left side, because then it's less than the key in the node. So we have to apply it in the left, and if it's bigger than, we need to insert the node in the right, like as the right child of that node, and then we just return the node again, and we have now inserted the node in our tree. So we can also like find some min values, which I'm not really going over in depth in this video here. And we can also have this function here deleting, how we can delete a node. So again, it takes a node or like a tree that we want to delete a node from, and then it takes the key, like the one that we want to delete from our tree. And then if our tree is empty, we just return the root node, and then we just want to find the node that we want to delete. So first of all, we're going to check if our the key that we want to delete is in the left subtree or in the right subtree, and then we can make a recursive call to that function again, and then we can go down in the left subtrees or right subtrees depending on where our key value are in the tree. And if the node is with only like one child or no children, then if the left pointer or like the left child is equal to null, then we just like free the root node here, and we return like the right child, or else we return the left child here, and again if the right node is equal to null. So if the node has two children, then we have this min value here, which we didn't really go over, but it can be used for some different kind of stuff. But I just wanted to show you like how to implement the functions like insertion and deletion, like how we can insert and delete a node in C++, which were the operations that we went over in the slides with the time complexity as well. And then we can just like delete the node down here with the right here, and then we can call this function here delete the in order successor in our tree, and then we just return the root here, and then this root here will be it will be like the node that we deleted from our tree. Then we can have our main function down here, where we're going to use this insertion here, and our in order traversal, where we traverse through all the nodes in our tree, and then we can delete a node and see what happens. So if we run this program here, we can see that first of all we're doing this in order traversal. So we're first going through 1, 3, 4, 6, 7, 8, 10, 14. So we're going through the left subtree first, and then we're visiting the root node, and then after that we're traversing the right subtree as we did in order traversal. And then after that we have now created this tree structure here, and then we can delete the node. So after deleting node 10, or like the node that contains the data 10 here, then we can in order traverse again, and we can see that we have now deleted the node 10 from our tree. So this is like how we can use these methods, like insert and deletion method in C++, and then how we can create a tree structure. So this tree structure can be used for a lot of different kind of things, and we've already been over in one of the previous videos with the priority queue, like how we can use a binary search tree for some more practical examples. So in the next video, we're going to go in more in depth with some of the other types of trees, with AVL trees and stuff like that. And they have some other different kind of properties that can be used in some other situations. So we're going to talk about that in the next video. So the last thing I'm going to say is just like thank you guys for watching these videos, and I just really appreciate your support. And remember to hit the subscribe button and bell notification on the video, and also like this video if you like the content and you just want more of it in the future. So if you want to apply some of these things that you learn in this tutorial here, I'm also like doing a C++ tutorial in computer vision with OpenCV, and also an artificial intelligence tutorial with some reinforcement learning currently. So if you're interested in one of those, like I'll link to one of them up here, and you can go check that out if you want to and apply some of these things, or else I'll just see you in the next video, guys. Bye for now.